Okay, so I'm going to talk about R and HPC and some some ideas that come up, some issues that come up when we're scaling. And so here's my brief outline. I'm going to just do a quick note about expanse, R and scaling, parallel R, and then embarrassingly parallel R. And I'll try to sort of organize these things around kind of like practical advice. So just a quick note about expanse in case you haven't used expanse or you're new to HPC. Expanses are a high-performing computer. There's 728 compute nodes. Each node has a bunch of cores. Each node has a bunch of RAM. There's also GPU nodes that are part of expanse. I'm not going to talk about those in too much unless you have questions. There's a user guide on the website, which is pretty good. And there's a training catalog, list of events, and some videos and documents, tutorials that you can see. So if you are new, as Mary said, you could go to some of the seminars, webinars, and also go online. A couple different ways to run R. In just a second. So we can run R through batch commands, which is in our environment is called Slurm, which is like a resource manager. You write a script and your R commands are in there, and there's just a basic header, and that's how you get resources. You can acquire a compute node with the srun command. We'll see an example of that. In this case, you'll use a terminal window. We also have a GUI called we call it the Expanse Portal, and we can run RStudio through that. And we'll also look at an example of that. And there's more details in the user guide. You can also run R in a Jupyter Notebook, so you can also through the portal get a Jupyter Notebook. Now, I put this in parentheses because I've only used this once. I know it's there, but I just haven't used it much, so I'm not going to have any examples for that. Again, RStudio, if you're new to R, it's an integrated development environment. It seems to be the most popular way people are using R. And typically, you would be using something like this on your laptop, and then when you have a big data problem or a scaling problem, you end up doing, migrating to the HPC, and you could still use your RStudio environment. If you want to run R interactively on an Expanse through the command line, you can run this through a terminal window. Here's the commands. I'm not going to go through all these in detail, but we'll see that this would be this kind of steps you go through. Expanse is a system where you have to, you log into a login node, you acquire a resource, the compute node, and then you execute these commands to load the relevant packages you need to run. So this is examples with the line, this code here is showing that example. Why do we use R on HPC? If we're running R on our laptop, typically we run out of memory, we need more compute time. Why do we use R instead of other packages? R has certain strengths that I think lends itself well to scaling on HPC. So data wrangling is one. It used to be the case, I think R was probably better than Python, but now Python actually does have a pretty good facility for data wrangling. There are, the main reason I think people are using R and come to HPC is that there are statistical procedure implementations that are just done in R, and you're not going to find them in MATLAB or Python. So here's the some that I've come across, and there's probably a lot more. And if I kind of organize this into groups, I could say that the first set here are mostly things you find in inferential statistics, or if you're doing experimental studies, you need these kinds of techniques. The last three are also things you'll find in data science, machine learning kinds of endeavors. And some of these scale better than others. When it comes to machine learning models, R does have some pretty good implementations for certain procedures, but Python, if you're doing deep learning, you're going to really go towards Python. But with machine learning models, it might depend on the model. Python is getting better with some of their implementations on machine learning models, that's for sure. Okay. And if anyone is doing Monte Carlo chain stuff, there is a new package called Stan, which is something you would check out. Okay, so just in a nutshell, if you're trying to scale your computation R uses the linear algebra libraries for operations on vectors and matrices, and MATLAB and Python are the same. So if you ever, run certain operations on R and MATLAB and Python, they're going to run similar. R does have multi-core, out-of-core, multi-node, distributed data options. If you start using really large data, where you need lots of compute nodes, lots of space, you might want to look at Spark R, and that's what Mai is going to talk about, Spark. And there is a Spark R interface for everything she's going to talk about. And as I said, some machine learning model implementations are pretty good at R, and they might be using the parallel on the back end. So we'll get a sense of what that is. So just a quick note about optimizing R code. In general, if you have for loops, and you can, rather than have for loops that operate element-wise, you would want to operate on vectors. So for example, adding 2 vectors instead of doing a for loop, you would probably just want to add the whole vector as a unit. So that's the kind of thing where vector operations tend to be run better on HPC environment. Let's talk about multi-core processing. So there is a package called do parallel, and this provides the back end for a for each command, which will parallelize your script, or at least parts of your script. It's going to use threads across CPU cores to pass data and commands. And this also works for multi-nodes. You could, in principle, get a couple compute nodes and use the cores on both nodes and have one for each command, and it'll distribute the processing. And in that case, it's using threads within a CPU, it's using MPI, which is message passage interface, between nodes. So we're going to say a couple things about that. So let's look at how this works. So with R, if you're using R, if you're familiar with R, there's an install package command that you would do, and you would execute that once, and then it'll be available in your home directory. You call a library command to load that package, and then you register your cores. So register do parallel says, give me 24 cores in this example. You have some data frame that you're creating or reading, pre-processing, and then you're going to have some kind of commands you want to execute on this data, and we can use this for each command. And in this case, the for each command says, okay, give me 24 iterations of a loop, and at the end of the loop, combine everything with a row bind. So you have the option of specifying how to combine the results. And there's a do par command which will run it across the cores. If you just say do, it runs it seriously. You say do par, it'll spread it out across cores. And then you have your code, and the important thing is that your code, it runs independently. So every time it's iterating on number 1 or number 2 or number 3 up to 24, that code does not need to know what was happening in the other iterations. So that's the key part about being able to parallelize your for loop. But you have to be aware, because what's R going to do behind the scenes, it has to distribute your code and relevant data to each core. And so depending on how you write this, depending on your needs, sometimes R is good at memory management, and sometimes it's not that good at memory management. So I've had situations where it seems to copy a lot more data than you think you need in order for each loop to execute. So that's the main thing you're looking at when it comes to trying to optimize or profile your code and see if it's running efficiently. Okay, if we want to run multi-node, as I mentioned, you can pretty much do the same exact commands, except here you're allocating a cluster, and you would be do a slightly different, so you use this make cluster command. So if I had 24 cores on each node, and I had 2 nodes, that's 48 cores. So you say, okay, I have a cluster, and I'm going to register it. And then you use your for each command, your do par command the same way. But the thing you have to remember is when you're copying data across nodes, the communication costs are much, much higher than when you're within a node. So I have found that it's just, unless, it just doesn't really pay. It's really expensive, relatively speaking, to um, run R commands this way. So if you have if you really need to use a bunch of cores, you can do this. And maybe if you don't have that much data, it would work okay. But you might want to try to, optimize by either splitting it ahead of time uh, um, or different kinds of breaking up the problem if you can. So we'll talk about that too. Okay, so what I want to do is I'm going to just show you a couple slides on how this looks when we go into Expanse, and then I'll go into Expanse and we'll run it live. So if you want to do this, I have a little script called basically the test script, and you can run it through the command line. You would get into Expanse by using these kinds of commands. There's an srun command that allocates a particular resource for you, and you have all these specifications about time and memory. You would, in our case, we have some GitHub repo that's going to have the example. Oops. There's a module spider R. If you're not sure what modules to load into your environment, you do a module spider R, and it's going to tell you what to load. And if you do this, it'll show you, R. You would execute a module R command, module load R command with a certain version number. Okay. All right. So then you run your skip. That's how this would work through a command line. And what's nice to also do is if you log in to Expanse and look at the job that's running. So let's say you've got a node, and you can SSH into that node and run the top command. The top command is a command that will monitor execution of your R script. It'll show you the memory usage. It'll show you compute time. It's actually monitoring everything that's going on in that node. So you can use this to kind of evaluate how well your parallelization works. So as I said, if you're running and everything runs fine, maybe you don't need to do this, but if you're running and it seems to take a long time, you could run this and just check and see how memory usage goes. That's going to be that's typically your bigger issue with R is seeing if it's and not allocating too much memory. All right, so we'll also look at an example of that. And instead of the command line, you can also do this through the portal. And I'll go through these slides again real quick, and then we'll look at this. I'll try to do this live. So the Expanse portal, you can start RStudio. There's the links. And I said you could also log into Expanse to get the command line. Here's what it looks like when you get into RStudio through the portal. There's going to be a dashboard page. You select your interactive apps, and so forth and so on. And then there's a form you fill out which asks you what resources you're looking for, and it's basically the same options that you get with a Slurm batch script. So I have an example here. You would say like compute node is a full compute node, the number of cores, the number of memory. If you're using a shared node, you're typically going to get less than 128 cores. The less cores you get, the more likely you'll get them faster. So I like to run with like 16 cores, for example, or 8 cores, and then I usually get 2 gigabytes of memory for each core. Okay. All right. So let me switch screens here. Okay. So this was the Expanse portal. And it's going to ask you for an access ID or some other way. There's a couple of different ways to log in. I log in through my access account. And if you're not sure what an access account is, that's the account that gets you the NSF resources. Again, the user guide will have information on that. Here we select RStudio as the interactive app. And it's going to ask me for this information about what partition you want. I have a particular reservation. You probably won't have that. Your account, your working directory, your time, and so forth and so on. So I'm not going to launch this now. I already got this launched, and there it is. And in fact, I'm already running it right here. So I have this little R script. Let me just show you real quick. It says, okay, give me, load the library, do parallel, register some cores, make up some data. Here it's 10,000 rows by 200 columns. Make up a linear regression, make up some data for a linear regression problem. And let's do like a bootstrap regression. So we're just going to sample from the data, run our regression model, run the LM. If you're our user, you should be familiar with that. Just list out some memory sizes and just sleep for a little bit, and then I think that's the end of the loop. And you return some results. So at the end, I'm just going to return all the coefficient results and just combine them into a list. Then you can do whatever you want with the, your typical bootstrap regression kind of thing. So in my RStudio, I'm going to just source this. Okay, and it's running. And if I switch screens to where my top command is, oops. Okay, so there I'm running, oops, let me maximize the screen. Okay, so you can see my user ID, I'm running, what did I say, 16, and you see some R sessions in here, RStudio, so there's a bunch of, you see all the processes. If I do H, oops. All right, so you can go and toggle, in your top command, you can toggle things. So I hit the small F key and I can come over here and just say, I'm just gonna hit the space bar, it toggles last CPU used. And so I can see what CPUs, and there's all my R sessions. And so they're kind of going in and out of this list as, as different processes on the operating system are getting executed. And you can see that I'm using all these different CPU IDs, so they're running on different cores. And this is the kind of thing you would do just to make sure things are running. You could look at this total memory used. So I'm not using that much memory. And I think if I go back to my RStudio, so this only ran for, I had a sleep command, so it ran for 60 seconds. And if I go and create a bigger matrix, you'll see more memory get used, and so you can test this system out. If you ran this with too much memory, you would see the memory fill up in the top command, and then all of a sudden it would just it would stop. It would give you a segment fault. Okay, so that's the basic, basic logistics of using the portal. Let me go back to my slides. Okay, so that was R parallel. And just a quick note, so again, we're using R, you're probably, if you're familiar with R, if you're comfortable with R, if that's the thing you want to use, that's, that's probably because it's running packages you want to run. But if you had to choose from the beginning, like when should I use R, when should I use MATLAB, when should I use Python? MATLAB also has a parallel facility or a parallel toolbox. It's very similar to R. You declare a pool of resources, and instead of for each, you have something called a par for. But the thing about MATLAB, because it's based on matrix operations, it does have a way to work with a distributed array or distributed matrix. So you can take a big matrix and declare it to be distributed, and then MATLAB will automatically process things in parallel for you. Oops. Hang on a sec. Sorry about that. So if you're doing certain kinds of operations, you do MATLAB. MATLAB is very good for certain kinds of fields like signal processing, a lot of the matrix operations. I find MATLAB maybe has a little bit better memory management than R. Python also has a parallelization tools. It works a little bit different. Again, you're declaring some resources. In this case, the terminology is number of workers, which are basically cores. And then if you have a for loop, you can say, okay, execute some function for each iteration of this for loop, but you delay it. And then you tell Python how to combine the results. So Python's going to parallelize everything first before it actually executes it. And it's not actually going to execute it until you get to this later statement where you say, okay, go ahead and do the computation. So Python with Dask has this facility to basically do the same thing, but it has this built-in flexibility. And so that can be really useful. In certain situations, it can be more efficient because you can sort of load balancing. We'll talk a little bit about that, but you can sort of manage things more directly if you want to. Okay, so that was just a quick. I just wanted to get that out there because I think it's useful to see the comparison. Now, I have come across several situations where it turns out a lot of our processes, a lot of things we're doing in experimental studies, you can kind of work through your data by breaking your data into parts. So you can process different subjects independently, different parts of an experiment independently, depending on what your situation is. So if you can break up your problem, you can parallelize it in what's called an embarrassingly simple way. First, you split up your data into, let's say, n parts. And then you could launch n instances of your R script, one on each CPU core, and each instance would process just one or maybe more data sets. But let's say you have one data set and you're going to process each data set with the R script. So as long as that R script knows which data set is working on, you could just process everything independently, parallelize that. So this is the embarrassingly parallel way to do it, but there is a question, is that we have to now launch the R script and pass arguments about which data set to process. So remember, you have each R script here is exactly the same, and they're just going to look for an argument to tell it which data to process. So there's two ways to do that. One is the MPI run command. If you're not familiar with MPI run, MPI is the message passing interface. This is a command that basically launches instances of your program across cores and across nodes. It's kind of a standard tool. It's very flexible. There is also this parallel command, which is a Unix tool or GNU tool, I should say. And this actually might be simpler for you. I don't think it's as flexible, but let's look at examples. So imagine I've split up my data set. So here I'm just showing you an example where I have 4 data sets. If you do an ls command, you list out your data sets. These are the 4 data sets I got. So if I execute this command, and this is a Unix command now, I'm just using ls, and then I use pipe. This is the pipe Unix command, which means take your output of the ls, feed it to the next command. So the command to parallelize is called parallel, and it's going to work on that list of data sets. I use a J option that says, okay, run this on 4 cores, only 4 cores at a time. So you're only going to run four data sets at a time. And I have the R script command. The R script command just is a way to execute R commands, your R script from the command line. And then I have my R script. So the parallel command is going to take the file names, execute R script, whatever your script is, and pass it the file and pass a file name. So in this little R script, all I'm doing is taking an argument, and I'm just going to write out the value of that argument. So let's see what it looks like. If I run this parallel command, I just basically get, okay, I'm starting my script, and this is executing. So this R script is executing the first data set, the second data set, third, fourth. That's all it is. So this is a real simple way to parallelize your R script across cores within a node. If you want to go multi-node, I think there's a way to do it, but I actually haven't done that myself. So, okay, so that's the parallel command. The MPI command is a little bit more work, but also probably a little bit more control. So let's say you split up your data set in parts, you run an MPI run command. In this case, you're going to run a script. Here I said, let's run like a little Perl script. It could be a Unix script, it could probably be a Python script, and all you're going to do is get the CPU ID. So you're going to use an MPI command to say, okay, what CPU am I running on? Remember, MPI run is launching the instances, one instance per each CPU. And then you get the CPU ID, you pass it to your R script processes the data set. And so this little box here gets distributed across your nodes and your cores. You could do this in a Slurm batch script, or you could do this from the command line. If you haven't seen a Slurm batch script, it looks like this. You have these options to say how many nodes, how many tasks per node, and how many CPUs per task. So in our case of Expanse, we have 128 cores. So you say, okay, give me 2 nodes. Each one uses all cores and only 1 CPU. I'm sorry, there's 128 tasks. So MPI is going to distribute tasks and assign 1 core to each task. So it looks something like this. You have, a certain number of cores, and this process is getting repeated. And finally, you have to have some other way to combine your results. You can also do, the nice thing about MPI run is you can do these hybrid executions. So instead of using all cores, you can have 2 nodes, use 2 MPI tasks, and each MPI task is going to get all 128 cores. So this way, you could have an R script, one R script on each node, and each R script uses the do parallel command. And that would look something like this. I only have 2 boxes here that got distributed across nodes, but each of these scripts are now using all 128 cores. Okay. So that's the benefit of the MPI run command. You're going to have more control over how much you split up the nodes and cores. So I have found that these techniques seem to be, I don't want to say popular, but I've come across situations where people just really like this, and that's really useful. So just a quick example, couple examples, scaling the MC routine. Here was an example from someone from UC Irvine. They had a bunch of individual web activity. They were running an MC model on each individual. And then they had to combine results with a hierarchical model. So if you know anything about MC, it's like you wouldn't typically be able to split this up, but they had a special procedure so they could divide this up. And they were able to run a bunch of cores on that. So that was a long process. Here's a different situation where you had a bunch of user data on social media use. Again, they were using the MPI run command to parallelize it. But each subject had so much different data that it was hard to know how long each subject's model was going to run. There was a big variation in time. So what we did was we ran with a lot of cores for all subjects. There was something like 12,000 subjects. So we ran a lot of cores for just a short time, and then if the individual was done, we took them off the list. And individuals that weren't done, we would run longer runs, but then we could use fewer cores. So we were able to run fairly efficiently without wasting too much core time. If you try to run all 12,000 subjects at the same time, one subject might take 12 hours and another subject takes 20 minutes. And then so you have a core sitting there just wasting, waiting and wasting time. More recently, this was a project I was not involved with the details, but this came out just recently. There's a group here at UCSD. They were doing some gene expression prediction modeling using bioinformatic tools. And what they did is they said, okay, we're going to split up the chromosome into 22 jobs. So each one processing 1 chromosome. And within each batch job, they were using the do parallel to run the processing of each gene with 1 core per gene. So they were able to run something like tens of thousands of genes in a few hours this way. I'm not quite, and I guess they're even, so that would be 1 batch job for, maybe 1,000 genes or something like that. Okay, and that one just came out they just published a GitHub page, and they got a paper there, preprint that's there. Okay. So just to summarize, independent R sessions, packing independent sessions onto core, it's going to be more flexible when you have data management issues, large number of separate models, variation in time per model, or if you want to do hybrid, multi-node, multi-core scripts. Compared to the do parallel, there's probably going to be a little bit more programming. maybe some more pre or post processing you want to do. But in the long run, if you have the bigger job, if you can split up, again, the key is that you can split up the data somehow. But if you can do parallel, that means you have some independence between each of the iterations. So maybe that means you could run independent R sessions. So this is basically how you're scaling. Do parallel is great for simple parallelization. If you need more control or more management in some fashion, maybe you could break this up into independent instances. Okay. So just a final note on Expanse HPC. If you're installing R packages, you're typically installing in your own directories. Occasionally, I see that people, sometimes you have to be explicit with your install package command, but occasionally you have to compile something, and if you get an error, you probably want to call support. Packages, sometimes they require certain shared objects, and they don't compile well unless you have the right modules loaded. That's typically what happens. So if you ever have that situation, ask for support. Okay. And that is my end.
Thank you, Paul. That was really informative. I appreciate what you did. Go ahead and stop sharing, and we'll move on to Mai. If you have questions for Paul, put them in the chat, and he'll do his best to answer them today. All
Yeah.
right, Mai, with that, I'll let you get started.
Hey, thank you. So hopefully you can all see my screen and the slides and hear me okay?
Yep, yep.
Okay, fantastic. So I'm going to be talking about Spark. These are the topics. We'll start with some brief history. We'll talk about RDDs and data frames, which are the main programming constructs for Spark. We'll talk about Spark's design goals and the APIs that are available with Spark. And then we'll talk about the core engine versus the libraries that are available in Spark. And I'll go over briefly a couple of demos to show you, kind of an idea of how Spark can be used. So this is a lot of stuff to cover in, I guess, less than an hour. So, it'll be a brief overview, but hopefully it'll give you a good overview of Spark. Okay, so let's talk about a brief history of Spark. So Spark is a computing platform for scalable computing, right? So it's designed for big data workloads, so large scale, complex data. Spark has built-in parallelism and fault tolerance, and it can run on commodity cluster. That means it can run on just, your regular hardware. You don't need a supercomputer like Expanse, which is what we have here, to run it. Although Spark is flexible enough that you can run it on a supercomputer like Expanse. You can run it on, a cluster where you have several systems that are networked together, and you can also run it on your laptop as well. Spark provides interactive querying, interactive analytics, streaming processing, along with batch processing. So you have interactive processing, streaming processing, and batch processing as well. And the design goals of Spark are to provide computational speed, ease of use, generality, and a unified platform. And we'll talk about all of these things as we go through our discussion here on Spark. History on Spark. So this began as a research project that began at UC Berkeley's lab back in 2009. They published a paper in 2010, and then they contributed that to the Apache Software Foundation in 2013, so more than 10 years ago. So the Apache Software Foundation is the world's largest open source platform. And so Spark is open source, and that's one of the main benefits of Spark. But there is also a commercial version that is offered by Databricks, and Databricks is a company that was formed by a lot of the people that started the Spark project at UC Berkeley. Okay, so one of the main goals of Spark is to provide computational speed, right? So this is designed for big data workloads, so speed is essential. And the way that Spark provides speed is making use of in-memory processing. So it exploits memory to cache data. And if you have in a distributed system, you have several systems that are networked together, you have a lot more memory than in a single system, right? So Spark is able to distribute it, to exploit the distributed memory in your system. And so that means that intermediate results are written to memory whenever possible. It can also spill to disk, but it tries to make use of memory because, accessing memory is a lot faster than accessing things on disk. Okay. So let's talk about resilient distributed data sets, or RDDs for short. So RDDs are a central concept in Spark. So an RDD is an abstraction of data as a distributed collection of objects, right? So an RDD is a data abstraction. It's a programming construct for storing and organizing data. And Spark uses RDDs to distribute data and computations across computational resources. So if you're talking about a single node, Spark will distribute data and computation across all the available cores or the number of cores that you specify. If you have a distributed system, it can also distribute computation and data across the different systems, across the nodes in your cluster. All right, so let's talk about what RDDs mean. So RDD stands for Resilient Distributed Data Set, right? So first and foremost, it is a collection of data. So you can read data from your local file system. You can read data from a data store like HDFS, which is the Hadoop distributed file system. You can read it from a relational database. You can read it from an S3 bucket. You can also create an RDD from an existing RDD. All right, and then it is distributed. That means that data is divided into partitions, and these partitions are distributed across the computational resources in your cluster. And then it is also resilient. RDDs are also resilient. What that means is that the Spark engine provides fault tolerance to failures, right? So when you are processing a lot of data, if something happens and you have to, some partition gets corrupted somewhere, you can't really start from scratch, right? So you want your system to be able to recover from these failures in a very efficient way, right? And the way that Spark does is that it keeps track of the history of operations performed on each partition. So if that partition gets corrupted and it has to be recreated, it already has a history of these operations, so it can recreate that partition in an efficient way. And all of this, the collection of data, the distribution of data across your computational resources, and the fault tolerance, all of that is provided automatically by the Spark engine. Okay, and then, so RDDs are a very important programming construct. And when Spark came out, the programming construct that was available was just RDDs. And then later versions of Spark, they came up with data frames and data sets. So these are extensions to RDDs. So they provide higher level abstractions, better improvements, improved performance, and better scalability. Okay, and you can convert from a data frame or data set to an RDD, and you can also use data frames and data sets along with RDDs. So you can use both of them. But usually now when you program in Spark, you will tend to use either data frames or data sets. All right, so what is the difference between data frames and data sets? They're very familiar in many ways. They both have lazy evaluation, and they're both immutable, and we'll talk a little bit more about what those things mean. The data is organized as a collection of rows, and the main difference between data frames and data sets is that data frame does not provide static type checking, whereas data sets do. And so data sets are used in strongly typed languages like Java and Scala, whereas in languages like Python and R that don't do strong type checking, you will use data frames. And so in the demos that I'm going to go over, I'm going to be using the Python API or PySpark. And so we're going to be mainly focused on data frames. Okay, so how do you use data frames? the entry point to all functionality in Spark is the Spark session. So the first thing that you do when you write a Spark program is to create a Spark session object. And you create data frames through the Spark session object. Right. So what this code shows is that this is how you create that Spark session object. You can pass in configurations through a Spark conf object, right? And you pass that through the Spark session object in order to set some configurations like the name and some options like how much memory do you want to use. And note that by convention, the Spark session object is named Spark. Okay. So you can create data frames through that Spark session object, right? And you can do that by reading data from files in your local file system. You can create data frames by reading data from a data store like HDFS, the Hadoop distributed file system. You can read it from a database. You can read it from a NoSQL data store. You can read it from an S3 bucket. You can read it from lots of different sources. You can also generate data. So this is specifying 2 rows in the data frame. And then you can use the Spark session object to create a data frame from this data. You can also create a data frame by transforming another data frame. So if there's an existing data frame, and you can also create another data frame from that existing data frame. Okay, how do you process data frames? There are 2 main operations, transformations and actions. A transformation will create a new data frame from an existing data frame, and an action will run the computations that have been defined on a data frame and return some value. Okay, so here's an illustration that shows how, transformations, how you can perform transformations and actions on the data frame. So you read in a data frame, you perform some transformation on that data frame, and a new data frame is created. And then you can apply an action to that data frame to get the results back. Right, so an important thing to note is that data frames are immutable. Right, so when you perform some operation on a data frame, when you define a transformation on a data frame, the contents of that data frame is put into a new data frame, right? So to change a data frame, another data frame is created to hold the changed data, okay? And this is important because of the fact that you're operating on a lot of data, right? And so when you operate on a lot of data and you have, multiple copies of this data potentially across multiple resources, multiple computational resources, it's a lot easier to keep track of copies of the same thing, right? If you have copies of the same thing and, this copy has certain changes and another copy has, different changes, it's really difficult to synchronize all those changes. And so this is why data frames are immutable in Spark. Okay, another thing that is important about processing data frames in Spark is that transformations, or these operations that you define on the data frames, have lazy evaluation. What that means is that transformations are not immediately processed, but what happens underneath the hood is that a plan of operations is built instead, right? So this is a logical plan, right? So you perform this operation followed by this operation followed by this operation. So there's just a plan. And then these operations are actually not executed until an action is performed. In other words, actions force the computation of the operations that have been defined on a data frame. And the reason that this happens is so that you can, the Spark engine can perform optimizations when it generates the physical plan, the actual step-by-step operations that will be performed on a data set, right? And so this is important to keep in mind, because when you're debugging a Spark program or Spark code, you have to remember that when you define an operation or a transformation on a data frame, nothing actually happens until an action is performed. Okay, so transformations have lazy evaluation in order for the Spark engine to perform the optimizations that are needed at the end. Okay. So we can talk about a specific example to show how transformations and actions are used in Spark. Right, so word count is a canonical example for illustrating parallel processing. So it's sort of like your hello world um, of parallel processing. Right, so word count, it's a very simple concept. You read your data, and your data could be in several different files, and it can be distributed across multiple computational resources. And the task is simply just to count the number of times each word appears in your data set. Okay. Word count is usually implemented using what are referred to as map and reduce operations. So map and reduce is a programming model for parallel processing. When you have, when you're distributing your computations and your data across multiple resources. So it essentially consists of two operations. There's a map operation and a reduce operation. So the map operation will apply some operation to all data elements, and then the reduce will aggregate the results of those operations into some sort of result at the end. Okay, so here's a simple example of word count looking at the map reduce process. So here's your input, right? Your input is just a set of words. Your data is split into partitions so that you can divide up the computation across your computational resources. The map operation will generate a key value pair for every word that it sees, right? And the key value pair will have the word for the key and then the value of 1 for the value part, right? So this means that you see this word, this is one instance of that word, okay? That is followed by a shuffling operation so that the pairs with the same key are moved to the same partition. And then the reduce operation will just aggregate the sums of the values, right? So what this means is that in your data set, you see the word bear 2 times. You see the word car 3 times, and so on. Okay, and then you can combine the result to get your final result, right? So this gives you a count of every word in your data set, right? So that's what word count is all about. All right, so this diagram shows how word count is implemented using data frames in Spark. So you read in your data, that's your text data frame. Then you apply 2 operations, split and explode. Split will split your text into words, and then explode will put each word on a separate line, on a separate row. Then that becomes your word data frame. Then you can group by the words, right? All the groups, you group them together, and then you count. And that is your word count. And then you can write out the results. Right? And this is the code. This is PySpark code, right? So this is the Python version of Spark. So this is reading in the data, doing a split and explode to turn the text into words. And then you do a group by, group all the words together, and then do a count. And then you write out your results. Okay, very simple. Okay, so this is kind of the outline of the structure of a Spark program. So again, the very first thing that you need to do is create a Spark session. Then you create a distributed data set, right? So this is your data frame. You apply transformations as needed, and then you apply actions as needed. And then you loop through this and create as many, apply as many operations as you need, and then create as many data sets as you need. And then at the very end, you want to stop the Spark session. Okay. Here is a high-level overview of the architecture of Spark. So there are 3 main components. There's a driver program, there's a cluster manager, and there is the executor running on the worker nodes. Right, so the driver program is where the Spark application starts. This is where the Spark session object is created. So the driver program will work together with the cluster manager. The cluster manager controls the physical resources. So the driver program will have to work with the cluster manager to allocate the resources that are needed to do the actual work, right? And so that the resource is allocated to the executor running on a worker node, And the executor actually does the work, performs the task, and then communicates that back to the driver program. Okay. Another design goal for Spark is to provide ease of use. And so Spark does this by providing APIs in lots of different programming languages. So this means that a developer can write code in, the language that they are familiar with, they're comfortable with. So you can write Spark code using Java or Scala or SQL or Python or R. There are also interactive shells, which allow you to interact with the Spark engine, and that is available in Scala, Python, and R. Okay, so this gives you an example of, that word count example in 3 different APIs. So this is PySpark, right? This is the Python version. This is what we just talked about. So you can write word count in Python-like syntax. If you're familiar with R, then you will use Spark R, right? So if you're familiar with R, this should look very familiar to you, right? So it's very similar to PySpark here, but it just has the R syntax. And then this is Scala, right? So you can write word count in any of these languages, okay? I'm not showing Java here, but you can also use Java to write the word count there in Spark as well. And underneath all of this, the code is generated. Any one of these code segments here will be converted to RDDs underneath, and then the Spark engine will interpret, the operations that have been defined on RDDs and perform the actual operations on the underlying data. Okay, another design goal for Spark is generality. And so generality in Spark is achieved by providing support for different data sources. So you can read data from your local file system. You can read data from HDFS, the Hadoop distributed file system. You can read data from a relational database. You can read data from a NoSQL database like MongoDB. You can read data from Kafka, which is a distributed streaming platform. You can read from cloud-based storage like S3 on AWS and others as well. You can run Spark on different platforms. You can run it on Hadoop. You can run it on a Kubernetes cluster. You can run it on a cloud platform like AWS. You can run it on a supercomputer like Expanse, and you can also run it on your laptop. Spark also provides support for multiple workloads, right? We talked about the fact that you can do batch processing as well as streaming processing on Spark. And you can also run machine learning workloads. You can do SQL code, and you can do graph processing as well, right? So this is how Spark um, provides generality, and this is how it addresses one of its design goals. So another design goal is to provide a unified platform for different types of analytics workloads. So the way that Spark does this is that the Spark engine, the core engine here, provides the core capabilities for scalable processing, right? All of the distribution of data across computational resources, the support for fault tolerance, all of that stuff is provided by the Spark engine. And on top of that, Spark also provides these libraries which provide additional higher level functionality for different types of workloads. Right, so for example, one of those libraries is Spark SQL, and that provides support for structured data processing, right? So you can do SQL queries, you can create tables, all the things that you can do with SQL. And the Spark SQL library has APIs for SQL, Scala, Java, Python, and R. And again, if you write this in SQL or you write this in PySpark, the underlying code that is generated by the Spark engine is converted to RDDs underneath, and then the Spark engine will interpret that and perform the actual operations on the data. Streaming, Spark Streaming is another library that comes with Spark. So this provides streaming data processing capabilities. So this allows you to do real-time or near real-time analytics. And the way that streaming processing is implemented in Spark is it does this through what's referred to as structured streaming. So the data stream is divided into micro batches of data. So the same operations that you can use in Spark for static data, you can use for the data stream, because it's divided into these micro batches of data, and you can apply the same operations on these micro batches. And Spark Streaming has APIs for Scala, Java, and Python. Another library is the machine learning library. So this has scalable implementations of the most common machine learning algorithms and utilities. It has APIs for Scala, Java, Python, and R. And then you also have the GraphX libraries. So this provides support for graph computation, right? So it has special structures for storing vertex and edge information and operations for manipulating graphs. So there's the GraphX library, which is RDD based, and then there's a GraphFrames library, which is data frame based. And it has APIs in Scala, Java, and Python. Right, so in summary, Spark provides a unified engine for large-scale data analytics, and the design goals for Spark are to provide computational speed, ease of use, generality, and a unified platform for different types of analytics workloads. Okay, and then there's some resources here that you can check out if you'd like. Okay, and then I just wanted to kind of give you kind of an overview of the couple of demos that we're going to be going over. So this is how you would log into Expanse if you had an account on Expanse, and then in the terminal window, you want to add this path in order to have access to Galileo. Galileo is a utility for launching Jupyter notebooks on HPCs in a secure way. I'm sorry, was there a question? Okay. And then this alias here, I have an alias here for this Galileo command. And it just sets the account, the account, the reservation, and then what partition we're using, the CPU shared partition. We're going to be grabbing 4 CPUs. This is how much memory we're getting and how much time we're going to be holding on to that. And then this is just the single layer container that we're going to be using. And then to check for the jobs that you have running, you can use this SQ command. Okay, so the first demo is going to be a book, just some really simple operations on a book reviews data set. And what I'm going to do is I'm going to change the number of cores that are available to the Spark engine, and then I'm going to run it, and then we're going to note the execution times. And the way that you change the cores is in this, when you start up the Spark session object, you can change this specification here. So if you put in a 1 here, that means that you are telling Spark to use 1 core. If you put in 2 here, that means Spark is going to use 2 cores. If you put in an asterisk here, that means that Spark is going to be using all available cores. Okay, and so we're going to be changing that, and then we're going to see how that affects execution times. So in the notebook, I'm going to be showing the execution time is calculated, and then I'm going to be changing that, right, from 1 core to 2 cores to 4 cores, and then we're going to run that and get the execution time. If you were running this on your own, you would want to do this multiple times and get the mean and the standard deviation, because it depends on the workload on the systems, you could get different execution times. Okay, so that's one demo. And then the other demo is a demo that's going to show you how you can use PySpark for scalable machine learning. So specifically for cluster analysis. So in this demo, we are going to be using weather station measurements as our data. The task is to perform cluster analysis to identify different weather patterns. We're going to be using k-means, which is a very simple but very effective cluster analysis algorithm. And so we're going to be looking at that. And so the data set are weather measurements from a weather station on Mount Whitson, which is in San Diego. And the measurements that we're getting are things like air temperature, humidity, wind speed, wind direction, and things like that. There are 3 years worth of data, and there's a set of measurements every minute. And this is the source of the data. And then just for reference, this is Mount Whitson. So it's a little bit, we're kind of down here somewhere. So this is a little bit northeast of where we are. Okay, so here's an overview of the clustering demo. So we're going to start the Spark session, load the modules, load the data, read in the data, do a little bit of data exploration. We're going to prepare the data by dropping nulls and then creating this feature vector. This is what PySpark, the machine learning library in PySpark requires, is that you need a vector of all your features. And then we are going to be using k-means cluster analysis. And then we'll just evaluate the clusters by plotting the cluster profiles. And at the very end, we're going to stop the Spark session. All right. So here's some resources. All right, so I'm going to switch over to here to look at the demos, and I'm going to try to, hopefully you can all see that. I'm going to expand this a little bit, make it bigger, right? Hopefully you can all see that. Okay, so I'm going to just go over this kind of quickly here. So this is setting up the Spark session, right? So this is setting your configurations for your Spark cluster. And this is just starting up the Spark session. We are printing out the Spark version here. This is recording the start time, and at the very end, we're going to find the difference between, the time at the very end of the notebook and this start time. We're reading in data here. I have this set up so that I have a data directory in my home directory, right? And that's where I put my data files. And then we're just going to do a count, say count how many rows are in that data file. Then we're going to just show the first few rows. And then we are going to filter this data to just get the rows that have the word science in it, right? And then we're going to show that just the first 20 rows. And then we're going to see how many rows that is that have the word science in it. And then we are going to look at calculate the execution time. And then we're going to stop the Spark session at the end. Okay. All right. So here, at first, I'm going to just use one core. Okay. So I'm going to run all cells here. And this is running on just a single core. I'm gonna restart that again. Restart the kernel and run the cores, because if you don't restart the kernel, some of that data will already be cached in memory. So you're not getting the true execution time. So I restarted the kernel and run it through. And with one core, it's about 7.8 seconds, right? So now I'm going to change this to using 2 cores. And again, want to restart the kernel and run all the cells. And now we're running the same code, except we're using 2 cores now, right? So with one core, it was 7.8 seconds. With 2 cores, we should get something a little bit, it should run a little bit faster. Right, so now we're at 5.9, right, with 2 cores. Now let's see what happens if we go to 4 cores. So again, you have to restart the kernel and run all the cells. So it was 5.9 with 2 cores. Let's see what it is with 4 cores. Oh, 5.2. Right, so you're getting diminishing returns here, right? Because anytime that you have multiple computational resources, there's going to be some communication overhead, right? So depending on how large your data set is and how efficient the communication between these computational resources are, you're certainly not going to get linear speed up, okay? But that just kind of gives you an idea of how you can set the number of cores on when you're running Spark on a system. Okay, now the second demo here is going to show you how you can use PySpark for scalable machine learning. So let's see, I'm going to clear everything so that I can run things. So this is just setting things up. And we're just setting up, starting up a Spark session object. And we are getting, printing out the Spark version. And we want to import some libraries here. All right, and then we're reading in the data here. So what we're doing here is we are setting the schema. In other words, we're telling it what the data types are for each column. There is also a way for, you can also ask Spark to infer the data type for each column as well, but that of course it's going to take a little bit more time because Spark has to read in a few rows in order to kind of infer what the data type is. So if you already know in your data set what the data type is for each column, then you can specify it explicitly here. Okay, and then this is reading the data. So again, I have a data directory in my home directory, and that's where I put all my data. All right, so this is printing the schema. All right, so this is essentially the same as what we put up here, but if you had asked Spark to infer the data type, infer the schema, then this is a way for it to check. Here we are going to count the number of rows, right? So Spark is reading that in, and it's about 1.6 million rows, okay? And this is showing the statistics. Right, so we have air pressure, air temperature, wind direction, average wind direction, average wind speed, maximum wind direction, maximum wind speed, and then minimum wind direction, minimum wind speed, and then rain accumulation, rain duration, and relative humidity, right? So it will, this will calculate the mean and the standard deviation, the min and the max, and the count as well, right? And you can see that there are some nulls here, right? Because not all of these have the same count. So what we're going to do next is we will drop nulls. All right, so this is a way to drop NAs, right? So it's a way to drop nulls. And so when we did that, then we went from this number down to this number, right? Okay, and then we need to create a feature vector. So this is a requirement for Spark Machine Library. So these are all the columns, right? The input variables that we're using. We have to kind of squish all of those into a single column. And that's what this feature vector is going to hold. And we do that by using this vector assembler object. So that's what we're going to do, right? And so this is what we have now, right? So we have all of these things. They're all in the same column, essentially, right? So they're just delimited by this, but they're all in the same column because all of that needs to be fed into the machine learning model. Okay. Then we are going to scale all these features, right? Because you can see that they're on different scales, right? So here's the air pressure, here's the air temperature, and here is I think this is the average wind speed, right? So they're on all different scales. And when you do cluster analysis, you want to make sure that everything is kind of scaled the same way so that not one feature will dominate the results, right? So this is how we are going to scale that data. So we're using a standard scalar object. The input is what we just got up here, right? The input to the standard scalar is here. And then we are going to output it into this column we name features, right? And we are going to subtract the mean and divide by the standard deviation, right? So that's how we're going to scale our data. And this is what it looks like at the end, okay? And then we are going to do cluster analysis. Now, one way to do cluster, when we use k-means, you have to specify k, which is the number of clusters. So we can use this method called an elbow plot in order to determine what is reasonable as a range of values for k, right? So I'm going to start this up and running here. So essentially what you do is you vary the number of k, the value for k, which is you vary the number of clusters, and then you use some measurement to calculate how that is affecting your clusters. And here what we're using is WSSE, which is the within cluster sum of squared error. So what that does is it calculates the difference between each sample and the cluster center that it was assigned to, and then you sum that all up for all samples in a cluster, and then you also sum that up across all clusters. And as the number of k increases, you are going to this metric is going to decrease, right? And the idea is that you want to get to some point where it kind of levels off, right? And so here, if you look at this, that point is right around here somewhere. So, you could look at 10, 11, 12 as a reasonable number for k, the number of clusters. So in this case, we are going to be using 11, right? So we are going to use 11 for the value of k, and we're going to perform our cluster analysis using k-means. And then when that's done, we are going to output the resulting clusters, the cluster sizes. Right, so these are the clusters, and these are the means and the standard deviations for the means for the clusters, the different clusters. And then at the end here, we are going to generate cluster profile plots. Right, so I'm going to go through, step through these here. All right, so we have 11 clusters, right? And each one is in a different color, right? So this is a plot that plots all of them. So this is, we're plotting all 1, 2, 3, 4, 5, 6, 7 features, and these are scaled features, right? So these are standard deviations away from the mean, right? So 0 is the mean, and standard deviations away from the mean. These are all clusters that are plotted together. We can look at clusters that capture dry days. How do we know that? If we look at relative humidity, that is less than 0.5, right? So we're going to be looking at clusters that have relative humidity that are in this region, okay? So we can do that, right? So these are clusters that capture dry days, right? Because they all have relative humidity that are below 0.5. These clusters, on the other hand, will capture humid days. So these are the other clusters that have relative humidity that are greater than 0.5. Okay, and then similarly, we can capture hot days with clusters that capture air temperature that are greater than 0.5. We can capture clusters that have windy days. So maximum wind speed that is greater than 0.5, right? So these are really clusters that have really high wind speed. Okay, so this is how you can kind of look at different cluster profiles. Okay, and then you can save the model. Right, so you can save your model here, and then at the very end, of course, we stop the Spark session. Okay, I'm going to go back to my slides here. I guess that is the end of my presentation. So here's some resources that you can check out. Just there's a Spark website here. There's PySpark API, what the data frame Spark and data frame is all about. This is the machine learning library, and then this is the latest user's guide. Okay. Any questions? I guess we have a few minutes for questions.